We're back on the horse here for an exciting session. So our first talk is going to be by Zhengzhong Jin from Northeastern, who's going to talk about SNARG without random oracles. So the floor is yours.
Yeah, thanks for the introduction. So this is this talk is based on a line of work joined with Yael Kalai, Alex Lombardi, Surya Mathialagan, and Vinod Vaikuntanathan. Okay. So SNARGs is the following scheme between a prover and a verifier in the CRS model. So the prover tries to convince the verifier that some statement X is in some NP language L by sending some message to the verifier. And the prover is provided with the NP witness W. The specificness means that the size of this message needs to be much shorter than the original NP witness size. And we require the following properties of this protocol. So the first property is called completeness, and it says for every X that is in this language L, the only steady generated proof should always be accepted by the verifier. On the other hand, the soundness requires that for any X that is not in this language L, any efficiently generated proof should always be rejected by the verifier. And here, the soundness is defined in the non-adaptive soundness setting, which means the instance X needs to be chosen independent of the CRS. You can also define an adaptive soundness where the adversary is allowed to choose the instance X after seeing the CRS. So can we build SNARGs for NP? Previously, starting from the seminal work of Mikhaili, there's a long line, very influential work constructing SNARGs for NP. And some of them are even practical enough for practical implementation. However, most of those works are based on knowledge type assumptions, or their security is proven in the random Markov model. So how about standard assumptions? Can we build SNARGs for NP from standard assumptions? Previously, the Jin-Weeks impossibility suggests that it seems unlikely to build SNARGs for NP from from any falsifiable assumptions, unless the reduction time of your security proof is at least 2 to the instance time or the 2 to the witness. So here, falsifiable assumptions are the cryptographic assumptions that, given a potential adversary, you can run in polynomial time to decide whether the adversary's attack is successful or not. And most of the standard assumptions, such as learning with arrows, are falsifiable assumptions. So this impossibility result requires the SNARG to have adaptive soundness, and it also assumes a black box soundness reduction. So recently, there is a line of work overcome this Jin-Weeks impossibility and build SNARGs for NP from standard assumptions by using indistinguishability obfuscation. In fact, they achieve adaptive soundness. Okay. So they overcome this Jin-Weeks impossibility by having a reduction time that is 2 to the witness time. So on the positive side, for this SNARGs from standard assumption question, we do know how to build SNARGs for NP from standard assumptions, leveraging indistinguishability obfuscation. So all of those works relies on indistinguishability obfuscation. So how about more simpler standard assumptions, such as learning with arrows or decisional Diffie-Hellman assumption? So for those assumptions, what we know is we can construct SNARGs for some subclass of NP. So initially, so this series of works constructed SNARGs for bounded depth P by applying Finnish-Shamir to GKR. And we also know how to build a SNARG for P or batch NP from standard assumptions, from learning with arrows. And more recently, so the work by Braksky et al., they construct SNARGs for monotone policy batch NP from standard assumptions. So as you can see, all of those works can only support for some restricted subclass of NP. So the question is whether we can construct SNARGs for NP from simpler assumptions, maybe simpler than I/O. And another direction is, and one way to approach this question is whether we can expand the class of languages we can support based on simple standard assumptions. And hopefully, these two lines of work will meet in the middle, so we'll get SNARGs for NP from standard assumptions, from very simple standard assumptions. Yeah, so the question we ask is, can we build SNARGs for NP from better assumptions than I/O? Yeah, and one way to approach it is to expand the class we can support from simple standard assumptions. So why this is an interesting question? So why we are not satisfied with SNARGs for NP from I/O? So the first reason is that this is a fundamental question to study, because SNARGs is a fundamental primitive, and asking about the minimum assumptions of a cryptographic primitive is a fundamental question. The second reason is that in all of those I/O-based SNARG for NP construction, the CRS is a structured CRS, so it consists of some obfuscation of some programs. So it needs trusted setup. So by developing new constructions of SNARGs, maybe we can avoid such trusted setup. And the final reason is currently we don't have good post-quantum I/O candidates. So by constructing new SNARGs, maybe we can have post-quantum secure SNARGs. So next, I'm going to first focus on the second direction. Yeah.
When you say you have no post-quantum, you mean under standard?
Yeah, under standard. So from standard, post-quantum secure
Yes, good and good. That's the good.
Okay, so first I'm going to talk about our result in the second direction. So can we build? So in the second direction, we stay in the simple standard assumptions, and we want to build broader class of languages that we can support. So we show we can build SNARGs from learning with arrows for any NP language that has a polynomial-size propositional proof of non-membership, where in the construction, our SNARGs has a uniformly random CRS, and the proof size is a fixed polynomial in the security parameter, but the CRS size will grow with the propositional logic proof. Okay. So crucially, the construction of these SNARGs doesn't rely on the propositional logic proof of non-membership. I will explain to you what is this propositional proof of non-membership on the next slide.
Can I ask
Yep.
But you need to know the length of that proof in order to set up the CRS?
Yes.
So you use the proof in that way, in like knowing the length?
Yes.
Or guessing or something?
Yeah, we just need the upper bound for the propositional logic proof. So the logic proof will only be used in the security reduction, but not in the actual construction. Indeed, in our paper, we also extend this result to a setting where you only have an upper bound on the space complexity of the logic proof, and the CRS size will only grow with the space, and not the polylogically on the length of the proof. Okay. Yeah. So what is this propositional proof of non-membership? So what we require is the following. So for any NP language L, for any X that is not in this language L, we require you have a polynomial size propositional logic proof for this fact that the relation circuit C with X hardwired is functionality equivalent to 0. So in other words, for every witness W, C of X equals 0, C of X and W equals 0 has a polynomial size propositional logic proof.
Subclass of one.
Right. So this is a subclass of NP, capital NP. So this seems a little restricted if you see it for the first time. But we will show very soon that in our second result, the same construction in this result can be proven soundness for every NP language under some stronger assumptions, such as witness encryption. Okay, so in our result, we use this propositional logic proof. So what is this propositional logic? So here, I will show you the definition of propositional logic proof by using the non-membership of some instance X. So given some NP relation circuit C, and its input is X and W, and let's denote the output wire as C out. Okay. So propositional logic proof of non-membership for some instance X is a sequence of Boolean formulas. It's a sequence of Boolean formulas from theta 1, theta 2, etc. to theta t. And each formula theta I are called lines in the proof. And they are just Boolean formulas. And each line theta I need to be derived in either of the following three cases. So either theta I need to be a promise, which means it asserts the correctness of a gate in this circuit computation. So each theta I can be a line saying this gate is computed correctly. For example, here is an AND gate in the circuit. The input wires are A and B, and output wire is O. And each line theta I can be a line saying this output O is computed correctly from A and B. And in the second case, theta I can also be derived from an inference rule, so which means there exists a constant number of previous lines from theta 1 prime to theta C prime, such that the current line theta I is derived from those lines. So by derived, we mean you can get theta I by only looking at this constant number of previous lines, which means this is a tautology. And finally, in the third case, theta I can be an extension rule, which allows you to introduce a propositional variable that has not been appeared in the derivation before. So here, this extension variable, this extension rule allows you to introduce a variable E, and the value of it is set to be some formula phi. So every line in the proof need to be derived following those rules. And finally, the last line in the proof need to be the theorem statement itself. And in our case, we want to prove the non-membership of some instance X. The last line of the proof need to be C out equals 0. So this will encode the information that for every W, C out is 0. Okay. So this is the propositional proof. And recall that our first result shows you can build a SNARG for NP based on learning with arrows, assuming the language has a propositional proof of non-membership. Yep.
Again, so when you say the language, you mean that for every no instance there must be. So you cannot restrict the result to in an instance-based way. Like you might have some instances presumably that have such a proof, but maybe some others don't have it. So some no instances.
Yes. Yeah. So yes. So you can either require the language has this property. So you require the language satisfies for every instance X that is not in the language. You have this polynomial-size proof of non-membership, where you can think of a general language, but you can only prove soundness for certain instance that has this property. Yep.
Can you a question about the previous one?
Yep.
So each of these data is what? It's a circuit. It's a clause.
So each theta is a formula. It's a Boolean formula. Yeah. So
Constant size Boolean formula.
So yeah. So in fact, we need the constant size Boolean formula, but with the extension rule, you can always break down a polynomial size Boolean formula to a constant size formula.
So what does it mean? Is that formula equals to 1? Every line is like that formula is 1. That formula is 1.
Yeah. So each formula, you can think in that way. So each line means that line is true, which means if you evaluate that line, you will get 1. Okay. Yeah. So why this result is interesting? So in our paper, we show some example languages that this SNARG can support. For example, we show it can support DTH language. But what's more interesting is that the same construction in this result can also be used to answer the question from the other direction. So, which is whether we can build a SNARK for NP from a weaker assumption than I/O.
Can I just make sure I understood correctly? You have some construction. You can prove it secure for any language in NP under an assumption that is worse than standard but better than I/O. The same construction you can also prove from standard assumption, LWE, if it happened, not for every language in NP, but only for those that have the property with a short proof.
Correct.
But it's all the same construction.
Doesn't the CRS size need to change? Because you said it corresponds to
the CRS size is still large. The CRS size is still so in both construction, the CRS size is large. It might be large.
And then it seems like your result needs to get around the Gen3X barrier, no?
So
it's in the previous one.
It's in the non-adaptive setting.
What was your answer? Say that again.
So
I heard the question, but I didn't hear the answer.
So the question is whether the CRS is whether there is some difference in the CRS size. So in both construction, the CRS size will be large in general. Right. So CRS size will grow with the propositional logic proof size. And the second question is whether it gets around Gen2X. It doesn't because we are in the non-adaptive setting.
Non-adaptive.
Yeah.
Thanks.
And in the second construction, the security reduction time will be 2 to the witness time. So it doesn't overcome Gen2X. Okay. So in our second result, we show the same construction is indeed secure for general NP language, assuming learning with arrows, and the existence of 2 round arguments for NP, where the second round message is succinct. Okay. So here is a 2 round arguments. So the verifier sends the first message, and the prover sends the second message, and we require the prover's message is succinct, which means it's much smaller than the witness size. And we allow the verifier to be private calling, and we allow the first message sent by the verifier to depend on the instance. Okay. So in this construction, the CRS is uniformly random. The CRS is transparent, and the soundness is non-adaptive. So this construction is universal, which means the construction doesn't need to use these 2 round arguments. And our construction is secure as long as there exists such a secure 2 round arguments for NP. So the 2 round arguments and its security is only used in the security reduction. Okay. So now you may wonder, what do we know about these 2 round arguments for NP? So indeed, any designated verifiable SNARGs can imply such 2 round arguments for NP. And also, if you have a witness encryption for NP, you can construct these 2 round arguments. So the idea is, if you have a witness encryption, then you can have the verifier send a ciphertext of some random message, of a random bit. And then you ask the prover to decrypt the message and send back the message. Then the verifier check if the message is correct or not. So this assumption seems to be, this witness encryption assumption seems to be weaker than I/O because it is a all or nothing kind of cryptographic primitive. It corresponds to non-I/O. And moreover, we know candidate constructions of witness encryption from evasive LWE and the LWE.
Can you say again why it's considered to be weaker than I/O?
So it's intuitively weaker than I/O, but yeah.
Yeah, no, but you said something about the intuition which I didn't get.
So the intuition is witness encryption corresponds to non-I/O. So you only obfuscate a program, and you only get security when the circuit is functionality equivalent to 0. So when the circuit is not functionality equivalent to 0, you don't have any security guarantee. You only have correctness. Right. Yeah. So in our result, we require these 2 round arguments to have a completeness proof in this extended frag system, in propositional logic system. And we require this proof to be polynomial size. Okay, so now you may wonder, what do you mean by, so what does this requirement mean? So what does this completeness has a polynomial size extended frag proof mean? So next, I'm going to tell you how to formalize this completeness property of two-round arguments in extended frag. So given any NP language L with a relation circuit C, we can formalize a two-round argument by denote its first round message as generated by some generator algorithm G with private random coin R. And the prover algorithm is P. It generates some proof pi. And the verifier verifies the proof using its private random coin R. So to formalize this completeness property, we just write down the completeness. So we say for every instance X and the witness W, if C of X and W equals 1, and this first round message Q is generated honestly by the verifier, and the prover generates this proof pi honestly from the first round message and its witness. If this condition holds, then we require the verifier accept this proof. So then we can formalize this completeness as a Boolean formula. And the requirement just requires this Boolean formula to have a polynomial size extended frag proof. So recall that our result is as follows. So if you have two-round arguments with this polynomial size extended frag proof, then we can have SNARGs for NP. So now you may wonder what kind of two-round arguments will have this polynomial size extended frag proof. So how should we understand this constraint? So next, I'm going to argue that this polynomial size EF proof constraint is almost for free, which means if you have a natural construction of two-round arguments for NP, then you should almost always have this property. So this is not a harsh constraint. So the reason is as follows. So usually when we construct a cryptographic primitive, we usually write down a mathematical proof to convince ourselves that this cryptographic scheme is correct. So, and the next step, so if you look at this mathematical proof, we usually use some basic arithmetics, such as addition, multiplication, etc. And usually in the mathematical proof, we usually just rely on their basic properties, such as abelian property of addition or the distributive law of multiplication. And by the proof complexity literature, you can translate all of those basic properties of arithmetic to polynomial size EF proofs. Yeah, so you can use the resulting proof complexity as a library to translate them to polynomial size EF proof. Yeah.
So you're assuming perfect completeness?
Sorry?
One imperfect completeness?
Yes, right. Yes. Yeah.
When you say polynomial size proof, polynomial in what for this specific?
Yes, good question. So we require that if A and B is represented as n bits, you can then you can represent this A and B as variables from A1 to AN and B1 to BN. We require the size of the translated proof to be polynomial in n.
But for the entire argument, so
the entire argument. So we want this right. So it's a length of this x. So you can imagine x is indeed x1 to xn because, yeah.
Oh, so you prove for, would you need a proof that for any xw this is true, or for any x and w you should have a proof? Which one?
So for any, okay. So in fact, x is fixed. What you need to prove, you can imagine x is fixed as some constant. What you need to prove is for every w, this holds.
So the proof is for a statement with a universal quantifier, right?
Yes.
with a specific x, but a universal quantifier on
Right.
w.
Yeah, for specific x and for all w. So in propositional logic, we don't have quantifiers in propositional logic, but
Yeah.
it's implicit for every w.
Like, can you prove something like smallness of values, like noise of lattice construction?
Yes, you can. The inequality can be formalized in those proof complexity works. Yeah.
Can you deal with like recursive constructions where
You can.
it uses kind of a circuit implementation of an algorithm, and you need to say circuit is the same as the algorithm?
Recursive algorithm you can, but you need the algorithm to be polynomial time. So you need the depth. You need to bound the depth of the recursion or the runtime of the algorithm.
So what's something that is natural and wouldn't fit well within this?
Right. There is good question. There are some example of language such as the yes, such as this the correctness of so it's unlikely that you can formalize the so it's unlikely you can using this method to get a polynomial-size EF proof for the correctness of this AKS prime testing.
Because like what doesn't fit? Is it the reasoning about probabilities? Is it
So the
generalization?
I don't know the detail, but the probably is because in the correctness proof you need there is some steps that may require exponential number of steps if you translate them to EF.
Because they use complicated algebra, which we haven't proved to have a short proof.
Yeah, we also don't know how to prove Fermat's Little theorem using this method. Thank you.
Could you use induction, for example, as part of an extended paragraph?
Yes, you can do induction, but you need to use a particular type of induction. So it's called polynomial time induction. So basically, the idea is you can only do induction on the length of those variables, but you cannot do induction based on the value of those variables. So the length will be n, but the value will be 2 to the n. So our work. So after our work, so here is the current landscape of this problem of SNARGs from standard assumptions. So our first result shows that you can build. So our first result only uses LWE, and we can only handle languages with polynomial-size EF proof of non-membership. And indeed, it can capture. If you look at this construction in the right way, it can capture all of the previous SNARGs from standard assumptions. And on the upper side, we know, our second result shows you can construct SNARGs for NP from only witness encryption, or DV SNARGs with this polynomial-size EF proof of completeness or correctness.
Is it possible or likely that every language in NP has such a 2-argument proof with a short extended Frege proof, etc., and then your result would collapse to LWE? Or is that likely or possible, conjecture?
That's the hope. Yes.
Yes.
That's the question.
You're conjecturing
There's
right
no
now.
barrier.
Totally
No barrier.
conjecture.
I guess just following up, does that follow from like the IO from well-founded assumptions? Like under those well-founded assumptions, do we have this thing?
Yeah, you can. So as I just said, you can use witness encryption, and we know how to use IO to build a witness encryption.
And that all has the nice extended Frege proofs, right?
Yes. Yeah, in our work we show here as
Has such a
IO.
proof been ever written?
They wrote it.
Someone
Yeah, so
wrote
that
it?
was my question. Maybe, wait,
That it has a proof of correctness.
can I ask? I think my question is not do you hope to succeed with LWE? My question,
Any IO construction.
do you hope to succeed with LWE with the following path, proving that every language in NP has such a short 2-argument system?
No, because
No,
if it
that
has
cannot
a
be.
system, it isn't called NP, so that's...
Can't you? Oh, that's a subset of NP intersect co-NP?
Yeah, because it has a short proof.
Yeah.
Well, that's possible too, but...
Here, this is the universal argument, right?
Yeah.
But your assumption is using an argument for NP which is not universal, right? In the assumption, is the argument also universal, or is it for a specific language?
I see. So the universal just means the construction is universal. So it means the construction does not need to explicitly use this underlying two-round argument.
Oh, because it's in the reduction?
Yeah, it only appears in the reduction. The construction only uses on learning with error.
But then if, let's assume that I have a subclass of NP for which I have these two rounds argument, then can I use your construction and it would be secure only for my, it would compile anyway and be secure only for these languages?
So you can think of it this way. If you prove that our scheme is not secure, if somebody breaks the scheme, they essentially prove that there does not exist any two-message laconic argument of this for this language. Yes. That kind of proves it.
I think she's asking if the two-round argument is for L, do you get a snark for L? That's the question?
Yeah, I mean,
Yes, you do.
but I think like what you just say is the contraposition of what I said, right? Like, I mean, if there's like,
So it's true even language by language.
It would compile anywhere, but like would be secure if you know that there is a language.
I think it's an interesting complexity question. So I'm not sure if this. So by assuming the existence of such a proof system, maybe it's not in co-NP. Yeah, I'm not sure because you allow
that
the
again. Maybe it's not what?
Maybe it's not. So if you just assume a language that has this two-round proof system, maybe it's not in co-NP because you allow the private coins.
It's private coin.
Yeah, it's private coin. You allow private coin on the wire.
So you're saying it's a possible that every language in NP has this property?
Every language, I'm not sure. I don't believe every language has this, but it's just a guess.
Any language that what? Sorry.
So he's saying if every language in NP have this proof system with statistical soundness.
Oh, no, not statistical soundness, but you don't need statistical soundness.
No, whatever you need.
Yeah. Yeah, we believe there exists such a
for every language in NP?
Yes.
Okay. Because initially Tianchu was saying that means the language would be an NP intersect coin.
No, we believe there are actually NP complete languages that have this laconic argument.
All of NP.
If you wish to check it offline, I don't understand.
Maybe we can discuss offline. Yeah.
Having the two round, that's what I'm asking. But they don't recognize or might not exist for every language. There's no clear conjecture.
Yeah, so in this line of works, we usually rely on the propositional logic proof to prove the security of our construction. So now you may wonder whether these logical proof techniques are really necessary, or can we avoid them? So if you are here for the obfuscation workshop, then I already explained there is a beautiful duality between logic and computation. And so I want to use this duality to explain this question. Okay. So in the computational world, it's very common that we make a non-black box use of functions, which means we use their circuits to build new crypto. So it's very common that we use FHE to encrypt the circuit that implements some cryptographic primitive and build some new crypto. It's also very common in the applications of gobble circuits or in zero knowledge. And this line of work that leverages these EF proofs, extended frag proofs or propositional logic proofs. So this line of work can be also viewed as a non-black box use of mathematical claims. So the analog is as follows. So every circuit can be viewed as a way to implement a function. And the propositional logic proof or mathematical proof can also be viewed as a way to implement or realize a mathematical claim. So for example, in our previous work, we construct I/O for Turing machines by leveraging this mathematical proof of functionality equivalence. And there, the mathematical claim is the functionality equivalence of two Turing machines. And in our first result, I talked about just now, we leverage the mathematical proof of non-membership. So here, the mathematical claim is the non-membership of some instance X. And in the second result, we leverage the mathematical proof of cryptographic. We leverage the mathematical proof of the correctness of cryptographic primitives to build a new crypto. So, and I'm sure there will be more applications in the future leveraging this non-black box use of mathematical claims. Yep.
Another question. Are there examples of this paradigm where the underlying, let's say, proof system in the proof complexity sense is allowed to be computationally sound? Like, is itself a cryptographic notion?
Yeah, what does that mean?
Right.
Sorry, can you say it again?
Like, so this, for example, this extended Frege is some specific choice of kind of proof complexity system, right?
Yes.
And it has completeness and soundness in the statistical sense, in the sense that if the theorem is true, there is a proof in that format, and if it's not, then there isn't a proof in that format, period, right? Like, regardless. So are there situations where you could potentially get by with such notion of proof system, but where the security is only against efficient adversaries?
Yes, yes. So indeed, our second result can be viewed, can be reinterpreted as a method that leverages this proof system, but you add a crypto assumption in it.
Because my next point was going to be, maybe you can sort of recurse and say, look, maybe you can actually get SNARGs to prove these statements, and they're shorter, because you like these proofs to be short.
Yes. Yes. But yeah, it's a good point. Yeah, it's possible, but we don't know how to leverage it currently.
Because you could maybe construct a SNARG, maybe that's a simpler problem, and then you can bootstrap out of it.
Yes. Huh? Yeah, that's a good point. Okay. So, so to answer whether such a non-black box technique is really necessary, you can also draw the analog in the computational setting, where there we develop black box separation techniques to formally prove whether some non-black box use of crypto is necessary or not. So one interesting open question is whether we can formalize this question in the for this line of works. Can we try to prove some impossibility? And to prove this impossibility, we might need to use some series from model theory or proof complexity, etc. Okay. So in the rest of the talk, I'm going to show you more technical details. First, I'm going to show you how to obtain the first result, which is how to build SNARGs for languages that has polynomial-size EF proof of non-membership from learning with arrows. And the next, I'm going to show you the same construction can indeed be proven secure for general NP languages by assuming DV SNARGs and learning with arrows. Okay. So next, I'm going to show you how to. I'm going to first focus on the first result. First, I'm going to show you the main challenge in this work and how we overcome them. Okay. So the main challenge of this work is as follows. So our starting point is the Sahai-Water SNARG from I/O. So recall that in Sahai-Water construction of I/O, inside of the CRS, there is a obfuscated program that verifies the NP relation. And if the relation verifies, then it outputs a signature on the instance X. So the honest prover just upload this instance X and the witness W and run this obfuscated program and get the signature. Then the prover sends the signature to the verifier, and the verifier verifies this signature. So our starting point is to try to instantiate this idea, not from I/O, but using FHE. So the starting point is to use FHE to encrypt a circuit, a relation circuit with X hardwired, and put it in the CRS. And the prover knows this witness W, so he homomorphically evaluates this circuit and obtains C of X and W. And then the prover just sends the homomorphically evaluated ciphertext to the verifier. The verifier at this point, the verifier holds the secret key of the FHE, and he decrypt and check if it's 1. So if it's 1, then the verifier accept, otherwise it reject. So of course, this construction cannot be sound because you cannot control what does the prover do. Maybe the prover just output a FHE of 1, then it can cheat. So we need to further attach a proof pi, and this proof pi will ensure this ciphertext is computed correctly. But note that we cannot use a very large proof. We need to have a very short proof pi. So again, we need the SNARG. So it seems that we are back to the beginning. Okay. Right. So at this point of the construction, the CRS, you can see the CRS depends on the instance X. And the verifier needs a secret key of the FHE to verify the proof. But I promise I will solve these 2 problems later. Okay. So previously we needed this SNARG to generate this proof pi. So what do we do? And the first attempt is just to use this bark construction from standard assumption. So recall that barks is, so if you are here for this morning, then you should already know what is barks. So barks is a SNARG for batch NP, where the prover tries to convince the verifier a batch of instances from x1 to xk are all in some NP language L. And the prover is given a bunch of NP witnesses from W1 to WK. And the succinctness only requires the proof size to grow with one of the NP witnesses. Okay. And the bark has this extraction property. So it has this argument of knowledge property, where the CRS of the bark has 2 different modes. And there is a trapdoor mode of the CRS, where you have index I embedded in it. So under this trapdoor mode, given any accepting proof, you can extract from this accepting proof to get the NP witness for the IS instance. And this idea can be generalized to some small subset of indices. So you can use this to extract a small subset of witness. But the proof size will, the cost of doing this is the proof size will grow with the size of the subset. And recall that previously, in the previous work, we used these sparks to build SNARGs. So the idea is as follows. So if the prover wants to convince the verifier that some computation is correct, let's say the computation is the computation of this relation, circuit C with X and W. So the prover just do this computation and record all of the intermediate wire values. And the prover generate a Merkle hash to hash off the intermediate wire values and get some hash root H. So this step is used to ensure the consistency when we later use sparks to prove the correctness of this computation. So the prover sends the hash root to the verifier and also attach a bark proof. The bark proof is for the following batch NP statement. So the instances corresponds to the gates in the circuit, and those gates are indexed by some variable. Let's call it G. And the corresponding witness for each instance G is the local opening to the input and the output wires of this gate G. So in this case, if the gate G has input wires and L and R and output wire O, then the prover need to prove there exists local openings rho L, rho R, and rho O for the input and output wires. Okay. And also he need to prove these wire values are computed correctly according to the computation. So the hash is just used to ensure between different instances. The hash is just to ensure that between different instances, which means between different gates, they are using the same wire values. Okay. Yeah, so the NP relation just verifies correctness of the computation and the correctness of the local opening. So we just apply this hash and bark construction to this homomorphic evaluation. So the prover knows this NP witness W, and he homomorphically evaluates this encrypted circuit on the witness W. So he gets a bunch of intermediate FHE ciphertexts. So for each gate, you get a FHE ciphertext. And the prover is going to use Merkle hash to hash off the ciphertext to get some Merkle root H. And again, this is used to ensure the consistency between different gates. So the prover sends the Merkle root to the verifier and attach the bark proof. So the bark proof proves that for every gate G, there exists local openings to its input and output wires. There exists the local openings correspond to its input and output ciphertext. And the output ciphertext is computed correctly using the FHE homomorphic encryption.
Sorry, I thought in Omer's talk, he said clearly that this is only secure if the reduction knows a preimage.
Yes, exactly. So that's the.
To prove about security.
So that's the
security net.
Oh, okay.
And we're not done with the construction.
Yeah. So this is just the construction. So the question is, how do we prove the soundness? It's not clear how we can prove the soundness, because barks only give guarantee that some subset of gates are computed correctly. Okay, so in fact, there is a barrier in proving soundness of this construction. The reason is that to prove the soundness of SNARGs, you need to build a reduction given any hypothetical adversary. So given any hypothetical adversary, the reduction should break the underlying assumption. So in this case, the assumption is LWE. But in the other case, for any instance X that is in the language, the reduction shouldn't break the underlying assumption because honest prover always exists. So you can always run in polynomial time and have the verifier accept. So in this case, when given the honest prover, the reduction shouldn't break the underlying assumption. So we have two cases. In the first case, when X is not in L, the reduction can break the underlying assumption. And in the second case, when X is not in L, in the second case, when X is in L, the reduction shouldn't break the underlying assumption. This seems to suggest that the reduction knows whether X is in L or not. And to know this, the reduction needs to run in the 2 to the witness time to decide the language. And indeed, this is the underlying intuition behind the Zhengzhong. So, right. But if we allow the reduction of time to run in the 2 to the witness time, then we will have a problem in the FHE security parameter, because we need to use complexity leveraging and set the security parameter of FHE large enough such that it's larger than the witness length. Then we lost succinctness. Because if you remember, the SNARG proof at least contains one FHE ciphertext. So if the FHE security parameter is greater than witness length, then the SNARG proof will also be greater than the witness length. So if you have tried to construct SNARG for NP from some assumption, then it seems that we always stuck at something like this. Okay. So can we avoid this 2 to the input length reduction? Can we have a polynomial time reduction? So our approach is to borrow the idea from the previous work of JJ22, and there the idea is to leverage polynomial-size EF proof of functionality equivalence of 2 programs to build I/O for Turing machines. But if you apply the techniques there, then given any polynomial-size EF proof of non-membership of some circuit C with X hardwired, then you will get a sequence of circuits from C1 to C poly. So you will have polynomial number of circuits. The first circuit is this C of X hardwired, and the last circuit is the circuit that always output 0. Moreover, if you look at any 2 adjacent circuits, you will see they are almost the same except for order of log n size subcircuits. And moreover, these two small size subcircuits will compute the same function. So that means for every gate, for example, for every gate here and here, they are exactly the same. And the only difference between any two adjunction circuits are in the subcircuit. And the functionality equivalence of these two subcircuits can be argued by only look at these two subcircuits. So this sequence of circuits is given by the previous work. So given any polynomial size EF proof, you can translate them to this sequence of circuits. And the number of circuits will also be a polynomial. So previously, GG22 leveraged this sequence of circuits to overcome this to the input length loss in the security reduction. The idea is for each intermediate circuit, we're going to build a cryptographic hybrid. And since the number of circuits is polynomial, the number of hybrids is also polynomial. And in the previous work, to argue the security, we use a puncturing argument. So we use a puncturing argument to argue that each two adjacent hybrids are indistinguishable. And we crucially relies on the functionality equivalence of these two subcircuits. Since we have this small security loss for every two adjacent circuits, and we have polynomial number of circuits in total, then the total reduction time is also a quasi-polynomial. So it's much less than the 2 to the input length, 2 to the witness length. But here, so in the previous work, we relies on this puncturing argument using I/O. We realized this, we proved this security using I/O. And in this work, we cannot use I/O. So the question is, can we do this from learning with arrows? Okay, so our approach is to realize these puncturing arguments using FHE. And the idea is as follows. So firstly, I'm going to add another FHE encryption of some circuit C prime instead of FHE, instead of the CRS. The reason is that I need to do this puncturing argument, I need to look at two adjacent circuits in this sequence of circuits. So I need to add a FHE of some other circuit C prime.
Why did you use I/O in the previous work? Weren't you constructing I/O?
Right. So in the previous work, we use I/O for circuit to build I/O for Turing machines.
Oh, got it. And now you don't want to assume I/O, so you cannot use it. Okay.
So I only want to use FHE to realize this approach. So I add some other FHE encryption of some circuit C prime, and the prover need to homomorphically evaluate this circuit C prime on his witness W and get some ciphertext. So prover also need to send some hash and bark to the verifier for this homomorphic evaluation. So at this point, the verifier has two independent FHE secret keys. And the puncturing argument we prove is the following. We show that for any C and C prime that are almost the same, except for functionality equivalent subcircuits, we have the property that if you decrypt, whenever you decrypt this CT1, if you get 1, then if you decrypt CT2, you also get 1. If you decrypt this CT2, you also get 1. And
sorry, can you repeat what the CTs are?
so the ciphertext, is the homomorphically evaluated ciphertext of this FHE1 given the witness W.
That's the output of the circuit, right?
Yes. Is the output of the homomorphic evaluation. Yeah. So we prove that if you evaluate T1 in the first FHE, then you must evaluate T1 in the second FHE. And crucially, we only use poly-security loss in this argument. Okay. So next, I'm first going to show you how to use this puncturing argument to prove soundness. Then I'm going to show you how to prove this puncturing lemma. So assuming this puncturing argument, we can prove soundness. The idea is, given this EF proof, we first translate this EF proof to a sequence of circuits, where each two adjacent circuits are functionality equivalent, are almost the same except for this small size subcircuit. And these two small size subcircuits are functionality equivalent. So, right. So given this sequence of circuits, initially, to prove the soundness, initially we have some adversary that breaks the SNARGs. So which means if you decrypt the first FHE, you will get 1. And now we can apply this puncturing argument to argue that if you decrypt another FHE, you will also get 1. So in the next step, I'm going to rely on the semantic security of the first circuit. I'm going to switch C1 to some circuit C3 in this sequence of circuit. So this relies on the independence of the two FHE keys. And after this switching, I can still argue when you decrypt FHE2, you still get 1. So then I can again apply the puncturing argument and go back to argue if you extract FHE1, you also get 1.
Wait, what was C3? Where did it come from?
So C3 is this sequence of intermediate circuits.
Right. Oh. In the proof.
Yeah, you derive this sequence of circuits from the EF proof. Okay. So now I can argue if you decrypt C3, you still get 1. If you decrypt the output of C3, you still get 1. And I can, using this method, to keep rotating the circuit in these two circuits. So in the end, I can get, if you decrypt the 0 circuit, you will get 1. But this reaches a contradiction because it's a circuit that just output 0. So in this way, we prove the soundness. Okay. So, yeah.
It makes sense to me, but it must be missing something. That puncturing argument, isn't that obvious? Aren't the circuits like just identical functionality?
So
they're the same everywhere except for a subcircuit that's the same functionally.
Right.
Isn't why is that not obvious?
It's so the point is that you need to prove this by only relying on the polynomial security of the underlying assumption.
Nobody's running the circuits. The prover's just sending you a succinct proof claiming that they ran the circuits. But you don't know what they did.
So the point is that these two circuits are functionality equivalent. But to check the, so in general, if you have two functionality equivalent circuits, to check the functionality equivalence, you need to run into the input length time. So it's not
your
clear
claim is not what's written there, but it can be proven assuming polynomial security.
So here we crucially rely on this subcircuit is small size. So the subcircuit only has order of log n size. So
it's because every step in the proof was small.
Yes, every step in the proof is small. So you can rely on polynomial security. Right. So I'm only going to show you a very high-level idea of how to prove this puncturing argument. So given any two circuits, C and C prime, and they are almost the same except for functionality equivalent subcircuit of very small size. I'm going to divide the circuit into 3 parts. So the first part is the gates that belongs this subcircuit. And the second part is the subcircuit. The third part is the gate that depends on the subcircuit. So I'm going to inductively prove from the input layer to the output layer that whenever you extract the same gate in these two circuits, you will get the same value. So of course, you can do this induction for every gate belongs to these two subcircuits because they are identical. Indeed, there are more technical details to control the arrow blow up, but you can deal with those details. So the second step is that we are going to use Spark to extract the entire subcircuit. And from the soundness of the Spark, we can ensure the subcircuit is computed correctly. And for every gate above these two subcircuits, we can also inductively prove that whenever you extract them, they are the same. So this is because the subcircuit is computed correctly, and every gate below these two subcircuits is computed correctly.
What is the error you're talking about?
Right. So you can imagine when when you go inductively from the bottom layer to the top, every time when you extract a gate, every time you can only extract a small number of gates. So for each gate, to argue is this, you obtain the same extracted value. You need to first extract the input wires of this gate. Right, but and then you need to argue these input wires are providing the same value. But then to prove this, you also need to extract their input wires. So you need a mechanism to save the progress you have made, and that is you can use the KR extension or the CDJ.
So you only use the smallest of the changes in step 2.
Right. So exactly. So I only use these small changes from this EF proof or this
Barks.
Yeah.
Barks.
Yeah. So the Barks proof can be short in the second step. Okay. So that's the high-level idea. So I'm short on time, and I'm going to explain to you in one slide how we extend this idea to argue SNARGs, the soundness of SNARGs for NP, assuming designated-verifiable SNARGs. Okay. So the idea is that so given any NP language, so for any NP language in general, for any instance that X that is not in the NP language, we have a 2 to the witness length EF proof of non-membership. So if you directly apply our techniques, then the number of hybrids will be 2 to the W. So our idea is to shortcut this exponential size EF proof. So by relying on the these 2 round arguments or designated verifiable SNARGs, we are going to first use the completeness property of the 2 round arguments to do some hybrid. And in one of the hybrid, we are going to rely on the soundness. And the subsequent hybrids will also rely on the completeness. So the point is that by using a soundness, which is a crypto property, we can shortcut exponential number of steps in the soundness proof. So in total, the number of hybrids will be polynomial. And the one interpretation of this method is to view this whole process as a EF proof augmented with some cryptographic action. Okay, right.
What Ali was asking, right?
Yes. So finally, here's a summary of our result. We built a SNARG for NP that has EF proof of non-membership. And we can prove security of it for NP from witness encryption or DV SNARGs, plus learning with arrows. Yes. And our construction is universal. And since we know how to build witness encryption from evasive LWE, we can build SNARGs from evasive LWE plus learning with arrows. Yeah, there are more results in the paper. So finally, some open questions. So the first open question is, can we close the gap between these 2 routes and obtain SNARG for NP from standard assumption? And perhaps a more approachable open question is whether you can build adaptive sound SNARGs from witness encryption. So yeah, so maybe one way to solve this is to apply the recent work of Waters and Wu. They build adaptive sound SNARGs for NP from I/O. So the question is, how do we apply their techniques here? Right. So also one takeaway of our SNARGs for NP construction is that by encrypting the circuit in the CRS, you can do something very similar to I/O-based construction. So basically, you can do some puncturing argument, and maybe you can use this puncturing argument and combine with Waters-Wu techniques to build adaptive SNARGs for NP. Right. And another question is whether the proof complexity aspect of those works are necessary, or can we avoid them? Yeah, and this is also related to whether Gentry weaks can be extended to the non-adaptive setting. And we have a recent work with Li and Chen. So we extend Gen2X to one query reduction setting, when the CRS is short. So maybe this. So if you think this EF proofs is necessary in this sequence, in this line of works, then this EF proofs should also. So then Gen2X should also be extendable to the non-adaptive setting. So yeah, hopefully in the future we can prove some statement about this. Okay, thank you.
Anybody has any questions? Actually, I guess I have to ask, is there something special about extended Frege, or could you use other proof systems that would also work?
Good question. So the property we rely on is the local property of extended frag. So in extended frag, each line only depends on constant number of previous lines, and that gives you the local property in this sequence of circuits.
I see. That's how you get your polynomial-size hybrids. I see. Yeah. Very cool. Any other questions? Okay. Yeah, please.
So can you maybe go back to the last slide? So eventually, like after using this more recent work where you somehow managed to jump between steps in the proof using this argument, what is your final requirement from the proof complexity? Like how long can the extended proof be?
So here we still require the completeness of this two-round argument to have a polynomial-size EF proof.
Okay, so this should have a polynomial-size proof, but the proof of the extended Frege proof for the non-membership can be as long as they want, or
So we need it to be. So in our paper we have two results. So one result, the CRS size depends on the size of the EF proof. So then the EF proof needs to be a polynomial. But there is another result in our paper. We show the CRS only depends on the space complexity of the EF proof, and it only grows logarithmically, polylog in the length of the EF proof. So the EF proof can be a super polynomial length, but the space of it needs to be a polynomial.
This is the one with the
both. You can always make the EF proof just grow with the space. It's like a general technique that you don't actually have to pay for the time.
Yeah.
If it's uniform, you can also just pay for the Turing machine sizes.
Right. So if your EF proof have a short description, then you only need to put that short description in the CRS.
Cool. Okay, well, let's thank the speaker. Okay, we'll resume at 3:30.